Myself, Dr. Nabamita Goswami, assistant. Sir, am I audible properly?
Yes, Dr. Goswami.
Okay, fine. Myself, Dr. Nabamita Goswami, assistant professor, electrical engineering department, NIT Agartala, Tripura, India. Today, I am here to present my paper entitled Surface Plasmon Assisted Wave Theory-Based Delineation in Multi-Gas Structure using Gold Nanolayer with Graphene, an approach towards biosensing applications. In this paper, my co-authors are written here. Now proceed to my research interest. My research interest is optoelectronics instrumentation, switching devices, fiber optic sensors, surface plasmon resonance sensor, biosensors, laser, and non-linear optics. These are the few things about me. Next, proceed to the state where our institute is situated. Our college, nationalist NIT Agartala, is situated in the capital of Tripura, which is one of the north state of India. Agartala is the capital of Tripura. Tripura is bonded with the north, west, south, and southeast by Bangladesh, whereas in the east it is the common boundary with Assam and Mizoram. Bengali and Kaupurk is the common language, and the instruction and the medium of instruction in the school is Bengali or English. Now, to explain this title, the contents are, these are the contents. In the abstract of this paper, we have written that we have designed one multi-layer structure having ZNO, AU, MOS2 and graphene nanolayer with 632 nanometer wavelength. We have detected the refractive index change of 1.33 to 1.45, having the resonance angle change from 57.7 degree to 69.8 degree with the desired sensitivity of 85 degree per RIU. With this idea expedites the new avenues in the field of biosensor and other industrial applications. Now proceed to few words about biosensors. We all know that a biosensor is a device to measure biological and chemical reactions with different concentration, having converted a biological response in electrical signal. These are the two examples. Now, elements of biosensors are analyte, receptor, transducer, and signal output. Now, if you proceed to the types of biosensor, then they will be categorized in based on the type of analyte and based on the area of application. Based on the type of analyte, they are enzyme-based, DNA, tissue-based, and immunosensors. In the area of application, they are electrochemical, wearable, physical, optical, potentiometric, nano, piezoelectric, immunosensor, thermal biosensor, and surface plasmon resonance biosensors. Now, sensitivity of this detection can further be increased using the phenomena known as surface plasmon resonance. Now, what a few words about what is surface plasmon? Now, surface plasmon is a collective oscillation of the free electron in the metal dielectric interface. We can create the surface plasmon by electron and by photon also. Excitation by electron is created by shooting electron into the metal. Excitation by photon require the coupling medium. Proceed to the second procedure, excitation by photon. These are the two examples of the surface plasmon excitation by photon. Now, in 1902, Wood discovered the surface plasmon phenomena. In 1968, Lord Rayleigh gave the physical interpretation of this phenomena. In 1968 onwards, we can find the product of surface plasmon in the market. This is the two experimental setup regarding this phenomena known as Plasmon configuration and another is auto configuration. Here, light will incident at a particular angle in the prism metal interface. Then, after creating surface plasmon, light is reflected from the configuration. This is Plasmon configuration where metal is directly deposited after the prism. This is the auto configuration where directly is deposited after the prism. Now, if we proceed to the physics of surface plasmon, then we can find that surface plasmon can be found in the copper, silver, gold, and sometimes aluminum due to their extraordinary property. If you see the periodic table of these metals, then we can find they have one electron in their outermost orbit and full 18 electron in their former orbit. Now, if we somehow excite this one electron, then one electron comes out, then full 18 electron are not further stable. Then they also comes out. Then we can find huge amount of electron in the surface. IP is the ionization potential to make free one electron from their orbit. This is 7.57 electron volt for silver, very less for silver. We can find huge amount of use of silver in the field of surface plasmon. Now proceed to the surface plasmon resonance. Resonance is the maximum point of the surface plasmon where the reflectance is minimum or zero. Now proceed to one side effect of surface plasmon resonance known as electric field enhancement effect, where the output light electric field is several 10 times greater than the incident light electric field. Here intensity is proportional to the electric field squared. This is the metal dielectric interface due to the creation of plasma, positive and negative ions are separated. Now, here all the analysis is done using the wave theory-based approach. The features of wave theory-based approach: to analyze the higher order modes within the structure, wave theory is more convenient and effective rather than the ray theory. This is the ray theory diagram. Now, similarity between the analytical solutions and the experimental solutions can also be achieved using the wave theory-based approach. This is a wave theory-based, and this is the wave theory diagram. Now, the proceed to the proposed configuration. Proposed configuration is about surface plasmon assisted wave theory based delineation in multi-layer structure. This is the multi-layer structure we have designed. This is the prism. When light incident at a particular angle in the prism SF10 and ZNO layer, then light will penetrate, creating the evanescent wave up to the biomolecule layer. After creating surface plasmon in the metal and dielectric interfaces, light is reflected from the configuration. These are the material specifications which we use to design the structure. Now proceed to the related equation used to simulate this configuration. This is the two-layer reflection coefficient. This is the related abbreviations used. This is proceed to the four-layer reflection coefficient. These are the related equations. Proceed to the, if beyond four layer, we need to use the transform matrix method for multi-layer structure. This is a multi-layer structure diagram, and these are the related equations. Now proceed to the COMSOL output variation of electric field within the proposed configuration with the change of the distance in x-axis and the z-axis. This is the diagram. Proceed to the alteration and the refractivity or the reflection phase as per the change of the refractive index of biomolecular layers and the resonance angle. If we see here, the refractive index is changing from 1.33 to 1.45, then we can find that the resonance angle shifted towards right, having the red shift. Now, alternation, this is a table for alteration of the resonance angle with the refractive indices. This is at 1.33, the resonance angle is 57.7 degree, 1.37, 61.1 degree, 1.41, it is 65, 1.45, it is 69.8 degree. Now, area of application of this idea: fiber optic sensor for refractive index measurement, refractive index sensing for environmental monitoring, then biomolecule medical application for refractive index sensing, refractive index sensing in microfluidic devices. Now, in the conclusion, we have written that one multi-layer structure has been designed with the prism, ZNO layer, AU nanolayer, and a MOS layer with a thin graphene layer at a wavelength of 632 nanometer, where the design sensitivity is 85 degree per RIU. Refractive index sensing is from 1.33 to 1.45, resulting the resonance angle change from 57 degree 0.7 degree to 69.8 degree. This idea expedites the new avenues in the field of biosensor and other industrial applications. These are the references which helped me to create this. Thank you all for listening me carefully.
Firstly, yeah, so I will start. Thank you. Firstly, thank all the organizers to inviting me for my presentation. Right now, I am DST Inspire faculty in the Department of Chemical Engineering and IIT Roorkee. And in line of the project, my work, which I am working currently, it's related to the international conference on composite materials. So I also synthesize some composite for solar fuel production, like CO2 conversion to methane or CO, and similarly nitrogen fixation to ammonia. So the first thing comes in the mind: why we want to utilize the solar energy, why it's important to our research area. The first thing comes in the mind is, whenever the light is coming on the Earth's surface, it has a different wavelength regions: 5% of UV, 45% of visible and infrared spectrums. To harvest this light, we need a semiconductor which can absorb the light. That will, this only semiconductor has that property which can provide the electron hole generation or transition of electron hole pairs. So there is a three class of metals: metal, is a semiconductor, and insulator. So semiconductor is important for harvesting the sunlight. So when we talk about the photocatalysis, so we need a semiconductor which can be acting as a catalysis. So this is the basic fundamental for the photocatalytic reactions. So now here, what I will show is what are the things that we are going to do it right now. The second thing is yeah. I don't know why I'm not able to. So this is the, so why CO2 conversion is important. There are n number of sectors like agriculture, electricity, industry, transportation that are generating the CO2 gases. And if you look the global mean average, it has increased tremendously from the past 4 decade. And if you look the past 5 years, it has been increasing a lot. And recently, the if we compare with the last year in December data of 2023, it's a 423.23 ppm. When we talk about a ppm, we see it's a very less amount, but generally in terms of ppm, 1 ppm is equivalent to 7.8 gigaton of CO2 in the atmosphere, 10 to the power 6, uh, 10 to the power 9, that is the equivalent CO2 release in the atmosphere. That's why this change is causing a various temperature effect. And as we are observing change in the climate or change in the pattern of the weather, so it's really visible to us. So now we need to act on the what are the sustainable way to convert CO2 or trap CO2. So these are the my basically research area. So when we do with the photocatalysis, so we make a thin layer, and onto the surface we absorb with the CO2. And the to want to convert CO2 into a methane or CO, we need a source of H plus ion to reducing agent. So we are using a moisture onto which we irradiate with the light, and it will generate a excitation when the sunlight energy and the light intensity is greater than the band gap energy. So here it's a conduction band region. Here the excess number of electron will be used for reduction reaction, while the valence band promote the oxidation reaction. And these reactions are multi-electron pathway that requires for a CO it requires 2 electron pathway. For methane it is 8 electron pathway for reduction reaction. Similarly, there is oxidation reaction happens also due to presence of force, and here the moisture will produce oxygen. And sometimes there is a competition between a CO2 reduction and the moisture to reduce to form a ORR or oxygen. So that is the main challenges of the CO2 or any photocatalytic reactions. And other than that, there are major limitation existing on the surface, that is the recombination events. So recombination event happen on the surface or even also in the bulk which generate the heat. So that's why it is a major limitation emerge as a photocatalytic reaction. So herein, I'm just trying one of my work where I took a gallium nitrate, put in the muffle furnace. So we prepare a gallium oxide. Then after we incorporated zinc nitrate, and onto which we prepare the gallium oxide and zinc nitrate heterostructure. Here it's visible, like gallium is matching with the JCPDS file of XRD, and similarly for the zinc. And when we make a heterostructure, the crystallinity maintained, and but there is a decrease of few peaks, and there is a formation of new peaks. That is validates the formation of heterostructure. After that, we added silver to absorb more light on the surface near NIR or that region. And the other thing that we observe in the next in figure B is CO2 TPD. CO2 TPD is a temperature program temperature desorption, temperature program desorption. Here it denotes the basicity present on the catalyst surface. So here at lower temperature, as we see, as we added the silver, the peak intensity increase in the lower region. It indicates that the basic sites available on the surface. Why basic sites is important? Because CO2 is acidic in nature, and if we need a basic, there will be a proper interaction, and more CO2 will be absorbed on the catalyst surface. So similarly, here the gallium oxide in the nanosphere mode, and we can see the lattice plane as well as the crystallite size and interlayer spacing. And similarly for the zinc, and in the next figure, we saw the heterostructure of zinc and gallium oxide. And when we coated with the silver, it around the periphery of the gallium oxide or zinc layers. So that is the change observed during a coating with the silver. So these are the HRTM results. And here we generally pass CO2 in the gaseous phase through a water bubbler and our photoreactor, which is a quartz reactor, and we coated one side with the catalyst and we irradiate with the light. And after a few hours, we collect sample and identify and quantify using gas chromatography. So what we observe that the CO is a two electron pathway which has been formed generally, but when we optimize the catalyst by adding a heterostructure or coating with a silver, it has been increased. Similarly, if we compare, because there is a competition between CO2 reduction and moisture reduction, because so these things are very important, and considering that silver is promoting the CO2 reduction efficiency rather than the moisture reduction. So that is the advantage of adding any plasmonic element, because it has also created the basic sites on the catalyst surface. Similarly, we collect the data during the in situ analysis of FTIR, we subtracted the spectrum from 120 minute and initial 5 minute, and we got the data of beta gallium oxide. And what we observed that there is a formation of different functional groups on the catalyst surface, that is a CO, CH bond, monodentate, bicarbonate, and OH radical, and COO minus. So there are in total 9 mechanisms for CO2 conversion. And according to these reaction intermediate peaks, we speculated the possible reaction mechanism for formation of the product like methane or CO. So these are the way, because the methane formation is the 8 electron pathway while CO is the 2 electron pathway. So these are the intermediates which are forming across the catalyst surface during the irradiations, like formaldehyde group or formic acid groups. So we try to investigate the possible reaction mechanism for the CO2 reduction reaction. Similarly, for the ammonia, like we put water, purge with nitrogen, mix with the catalyst, and irradiate with the light. Similarly, we observe the ammonium concentration. And what we observe that the silver coated on the heterostructure of gallium and zinc oxide promoting the ammonia formation. Similarly, we replicate the same experiment in situ drift, where we collect the data at every hours, 1 hour, 2 hours, followed by the third hour. And what we observe that the adsorbed moisture is decreased, which is the bending or stretching vibration of NH bond. And these are the isotopic level nitrogen gas, like 15 NO2. So it is giving the no artifacts or no interaction from the atmosphere. So that's why we have used isotopic level nitrogen gas for the drift study. And we observe the stretching vibration of ammonia group and bending vibration of NH group. So that this indicates that these catalysts are capable of breaking very strong or stable nitrogen into ammonia. So these are the some of the work that we did, and this mechanism will be like so following mainly associative mechanism. Here the nitrogen will be reacted with the proton and electron, and it will be converted into hydrogen group, and similarly it will form ammonia. So these are the things that we validated with the nitrogen fixation as well as for the CO2 reduction reaction. And the other thing which is very much important is, let's say if we are making a catalyst and we are synthesizing it, and there is interaction with the moisture, because the moisture is the source of H plus ion, and which is a low cost compared to other agent like ethanol, methanol, or say other sacrificial agents. So how it is interacting? So what we observe that from the contact angle measurement, that these gallium oxide and zinc oxide are hydrophilic in nature, super hydrophilic in nature. But even in the its heterostructure is hydrophilic in nature. Yeah, you see here is complete dissolve on the surface. But when we added silver, it has increases the basicity, also a sense of hydrophobicity, because it is hydrophilic in nature. It's not super hydrophilic. So what it will help, it will allow much more interaction of the adsorb CO2 and nitrogen on the bubble or on the catalyst surface. So that is a way of enhancing the interaction between the photoexcited electron and the adsorb species. So that is the reason mainly we are getting a maximum number of photo reduced product here in this case. Later on, what are the scope for the development for these catalysts? Like here we did with the gallium oxide, silver, which is also costly. So the scope of development will be a facet control, or any, if we can use any earth abundant catalyst, which can be useful for finding low cost catalyst or durable catalyst. And for the photocatalytic reaction, the most important thing is the band alignment and the wetting property. If we can make a more hydrophobic nature in the catalyst, photocatalyst, it will be enhance the interaction between the CO2 or any photocatalytic reaction. Similarly, this is a photocatalytic reaction, and the solubility for the CO2 at ambient condition is 25 gram per liter. Similarly, for nitrogen, if you want to make ammonia, it's very less. If we can increase the solubility by changing the reactor design or modifying its configuration, or we can increase the light illumination area or catalyst expose area. So this is the way where we can increase the product aid, because photocatalysis is still far from the industrial application and a lot of research is going on. So these are the research area where we are working on. Similarly, if we make a photoreactor with a solar cell connected, like photo electrocatalytic system, so that will be again a good approach for making a uh, CO2 reduction reaction or any photocatalytic reaction. Similarly, here we did in situ drift, but if we can integrate with the DFT and all other mechanism, so it will be helpful for understanding the reaction mechanism. So these are the previous research paper with we have published so far, in which one of them is also selected as a hot article by RSC, Royal Society of Chemistry. And thank you. If you have any questions, please feel free to ask.
Myself, Jyoti Sharma. I am assistant professor at UIT Punjab University, Chandigarh. The title of my presentation is Local Thermal Non-Equilibrium Effects on Instability of Hybrid Nanofluids. Let us start with brief introduction on natural convection or Rayleigh-Bénard convection. We have a horizontal fluid layer, and this layer is heated from below. And the fluid at the bottom becomes lighter than fluid at the top, and it tries to redistribute itself. So, and then viscosity of the fluid come into the picture. It tries to prevent the motion of the fluid, and after some time, fluid becomes unstable, and at the onset of instability, fluid layer resolves into number of cells. This phenomena was first observed by Bénard in 1900, and these cells at the onset of instability are called Bénard cells after his name. Theoretical interpretation of this phenomena was given by Lord Rayleigh in 1916, and the stability is determined by the numerical value of non-dimensional number called Rayleigh number. This Rayleigh number is the ratio of destabilizing buoyancy force to stabilizing viscous force. So this phenomena was studied for a regular fluid, and in this particular problem, we have this horizontal fluid layer. And this is, in this layer, we have hybrid nanofluid. Phi1 and Phi2 are volume fractions of two different nanoparticles. Temperature at the bottom of the layer is more than at the top. And we will be finding Rayleigh number for this system to check the stability of hybrid nanofluid layer under local thermal non-equilibrium effects. So for this, we have this set of conservation equations given by Born-Grenoux. These equations are modified for our system of equations. We have first continuity equation, then thermal energy equations, and then nanoparticle conservation equation. All these equations are based on various conservation laws. Then we have 9 and 10 boundary conditions to solve the system of equations. And then we introduce non-dimensional variables given by equation number 11, and then equations 1 to 10 are now reduced to non-dimensional form given by 12 to 18. And 19, equation number 19 is representing the non-dimensional numbers which are being introduced in the equations. And boundary conditions are now reduced to 20 and 21 in non-dimensional form. Now these equations are solved to find the expression for Rayleigh number. So for this, we have used these steps. We have conservation equations in non-dimensional form. Then we assume initial solution for this system of equations. Then we impose small perturbations on initial solution. And then these perturbed equations are solved using normal mode technique and Galerkin method to find the expression of Rayleigh number for our system of equations. And if this Rayleigh number increases, then system will become more stable. And if value of Rayleigh number decreases, system becomes less stable. So I'm not discussing all these calculations. After doing these complex set of calculations, we have this expression of Rayleigh number for our present system of present system. So this expression is very complex. We validate this. We put LTNE parameters equal to 0 in this expression, and we get expression for LTE case. Then we further, when we put parameters corresponding to second nanoparticle equal to 0, we get this expression, and this is very well known expression. This expression was found by first established by Nield. So in that sense, this our expression gets validated. So this is very complex expression. To analyze this expression, we used Mathematica software, and we have 6 non-dimensional number. We check the effect of those 6 non-dimensional number on this expression of Rayleigh number Ra. So in figure 1, we can see that as the modified thermal capacity ratio increases, value of Rayleigh number is decreasing. So this means system becomes less stable as the value of modified thermal capacity ratio increases. Then figure 2 shows the effect of Nield number. As it increases, Rayleigh number is increasing, so it stabilizes the system. Figure 3 shows the effect of thermal diffusivity ratio, which increases with the increase in its value of Rayleigh number is increasing. So these 3 non-dimensional numbers are due to LTNE effects, and these effects, out of these 3, 2 are showing stabilizing effect and 1 parameter is showing destabilizing effect. Then concentration Rayleigh number, this is introduced due to the presence of nanoparticles. It destabilizes the system. Lewis number destabilizes, and modified thermal diffusivity ratio has slightly destabilizing effect, which is not shown in the graph. So all these 6 non-dimensional numbers are introduced due to LTNE effects and hybrid nanofluid character of the fluid layer. So out of these 6, Nield number and thermal diffusivity ratio contribute to making the system more stable, while all other 4 parameters make the system highly sensitive. So to make this study more practical, we analyze the effect of physical properties using alumina and titanium dioxide nanoparticles in water. So figure 7 shows the effect of conductivity of base fluid. So as conductivity of base fluid increases, Rayleigh number is decreasing. And in figure 8, as conductivity of particle is increasing, Rayleigh number is increasing. So conductivity of base fluid and conductivity of particles behave in opposite manner. They have contradictory impact on the stability of the system. Then similarly, in figure 9, density of base fluid contribute in stabilizing the system, while density of particle contribute in destabilizing the system. So both density and conductivity have contradictory impact on the stability of the system. Then we check the effect of specific heat of base fluid, which stabilizes the system, while specific heat of particle do not have much impact on the stability of the system. Then variation of viscosity is shown in figure 13. Viscosity is found to be very important parameter, and as viscosity increases by small amount, there is a significant decrease in the value of Rayleigh number. So viscosity has a destabilizing impact, and volume fraction of particle has stabilizing effect. As we increase volume fraction of particles in the fluid layer, it is going to stabilize the system. Further, we analyze the problem in detail, and we considered different non-metallic and metallic nanoparticles in water and ethylene glycol base fluid. So figure 15 shows the effect of alumina and titanium dioxide nanoparticles in water, and figure 16 shows alumina and titanium dioxide nanoparticles effect in ethylene glycol. So in both the figures, we can see that LTNE curve is above the LTE curve. So this means LTNE effects LTNE model stabilizes the system more as compared to LTE case. And also we can see that alumina nanoparticles stabilize the system more than titanium dioxide. And when we further analyze the data, we found that alumina is more stable because of its higher conductivity and lesser density. Then we check the effect on alumina and copper nanoparticles in water and ethylene glycol. So copper is found to be more stable than alumina in water-based nanofluid, and it is because of its higher conductivity. While reverse order is observed in ethylene glycol. In case of ethylene glycol, we can see alumina is more stable than copper. And this is because in this case, density acts as the dominant property, maybe because of the different viscosity of ethylene glycol. Then we check the effect using two different metallic nanoparticles, silver and copper, in water and ethylene glycol. And we observe that silver nanoparticles make the fluid layer more sensitive as compared to copper nanoparticles. As copper nanoparticle curve is above the silver, so silver make more sensitive as compared to copper, and it is because of their higher density. Silver nanoparticles are less stable. So then we check the vertical axis. RF in case of water takes more values, higher values as compared to RA in case of ethylene glycol. This is because of its lower viscosity of water. It acts as more stable base fluid than ethylene glycol. And out of all the physical properties of base fluid, it is the viscosity which plays a significant role in the convection process of the system. Thank you.
Good evening, everyone present over here. Myself, FARHA, research scholar from the Department of Chemistry, Aligarh Muslim University, Aligarh. Before starting, I would like to thank the jury members for giving me this opportunity to present my work over here. My research area is concerned with the synthesis, characterization, and application of charge transfer complex. And the title of my current manuscript is Spectrophotometric Studies of Synthesized Charge Transfer Complex of 2-ethyl with 3,5-dinitrobenzoic acid, exploring its interaction with Bovine Serum Albumin, antimicrobial activity, molecular docking, and DFT, TD-DFT. Starting with the introduction of charge transfer complex. Charge transfer complex are formed by the transfer of an electron from donor to acceptor. The donor is electron rich and acceptor is electron deficient species. They are held together by hydrogen bonding. In the characterization, first of all, we have FTIR, and here the FTIR spectra of donor, acceptor, and CP complex is there, which clearly indicates the peak for NH static vibration at 3156 centimeter inverse. Second, we have performed the UV spectra in 4 different polar solvents, namely methanol, ethanol, acetonitrile, and DMSO.
Miss Farhana, sorry to interrupting. Your slideshow is now not visible. You go to the full slideshow. You changing your slide but not showing here.
Okay, so might be not a problem.
You go to the full slideshow in your screen.
So now it is visible.
Visible. You change your slide. No, not changing your slide. Go to slideshow from beginning.
I'm only the slideshow from the beginning. Is the problem solved?
Still not.
Okay, what shall I do?
You stop your sharing and again your slide sharing your presentation.
Okay.
And with the slideshow.
Okay, sir. So now, okay.
No, slideshow. Now changing your slide. Okay.
So next we have.
You go to the full screen, slideshow, full screen. Then it is clear to see. Yeah, very good. Nice. Go ahead.
Okay, next we have UV spectra in 4 different polar segments, namely methanol, ethanol, acetonitrile, and DMSO. With the help of this, we have determined the absorption at maximum wavelength. Also, with the help of Bensey-Heliband equation, we have plotted a BH plot, which is A naught by A versus 1 over T naught, which have in the determination of the stoichiometry of the complex. The straight line in the graph clearly indicates that the city complex is having 1:1 stoichiometry. Moreover, it also has the determination of various physical parameters like its energy of interaction, dipole moment, oscillator strength, etc. Here I have written the Bensey-Heliband equation and the plot is shown over here. To further validate the formation of city complex, we have undergone single crystal X-ray diffraction study, which clearly indicates the crystal structure. With the help of this, we can know that the crystal crystallizes in monoclinic crystal system having P2-1 space group and an empirical formula of C12, H12, and 4 versus. It also shows the energy bonding with having a bond length of 2.6 coded angstrom, hence clearly indicating the formation of complex. In the application part, we have explored the protein binding properties of the complex with the bovine serum albumin protein. For this, we have performed the fluorescence in UV study. The quenching in the fluorescence clearly indicates the binding of the protein with the complex. The fluorescence spectra of DSA were obtained at various concentration of the city complex. It is clear from the picture that DSA's intrinsic fluorescence gradually diminishes as city complex concentration rises. Furthermore, UV study technique exploits the absorption of UV light by aromatic amino acid and peptide bonds in protein, providing insight into conformational chain and binding events. To calculate the binding constant, we have utilized the Wilson Warmer plot, which with the help of this, we have determined the KSV value, which is found to be 2.3805 per mole. Next application, we have the antimicrobial study, where we have explored the antibacterial and antifungal activity of the complex using various bacteria and fungi. Bacteria, the E. coli, Bacillus subtilis, Staphylococcus aureus. The fungi are Aspergillus niger, Candida albicans, Fusarium oxysporum. Antibacterial and antifungal properties of the city complex were explored. It inhibits the growth by breaking the cell membrane and hence diminishing the bacterial growth. It also exhibits the exceptional antifungal properties. As far as the computational study are concerned, so to check the binding of the complex with the protein, we have performed molecular docking study. Here I have shown the best docking poles using helical model for the basic protein and the complex. Next, here is the 3D and 2D representation of the helical model. Second computational study is DFT study. It is a method of obtaining an approximate method using a Schrodinger equation. DFT is a computational study. Computational codes are used in practice to investigate the structure and magnetic and electronic properties of molecule, materials, and defects. These are the molecular electrostatic potential map, which illustrate the charge distribution of molecules three-dimensionally. It also shows the attractive and repulsive force felt by the fixed charge at various points in a space that are equidistant from a molecular surface. It can be interpreted as a map of electron access and electron deficient region. Next figure depicts the location of the HOMO and LUMO pairs, the HOMO-LUMO gap, and the corresponding energies for the 2-ethylmetazole, 3,5-dinitropentasic acid, and city complex. It was determined that the HOMO to LUMO band gap for the 2-ethylmetazole and 3,5-dinitropentasic acid and the city complex were 5.6422, 5.2985, and 4.5582 electrovolt respectively. To conclude, in the current study, we have synthesized a novel organic transfer complex, the donor acceptor moieties, being 2-ethylmetazole and 3,5-dinitropentasic acid respectively. FTIR and UV visible spectroscopy are to further spectrophotometric analysis that are used to further characterize the synthesized city complex. Using the plot and Denisi-Helical equation, a number of physical properties are determined and the stoichiometry is determined to be 1:1. The SCXRD analysis, which demonstrates the initial bonding with a bond length of 2.648 angstrom, provides additional validation for the spectrophotometric findings. The synthesized city complex interacts with PSA, as shown by the molecular docking, which validates the experimental findings. The molecular geometry of the city complex was investigated, the use of theoretical data drive complicated simulations. Additionally, the city complex has strong antibacterial and antifungal activity in addition to exhibiting remarkable pharmacology to its interaction with the PSA. That's it. Thank you.
What is photocatalysis? Photocatalysis is a process in which the light energy is used to pair the chemical reaction, means to drive the chemical reaction. In this process, the absorption of light can excite the electron hole pair is produced for use of light energy. And another thing is photosynthesis. In photosynthesis, solar light to convert the water and carbon dioxide into the oxygen and carbohydrate. These are the two methods. One is photocatalysis and second is photosynthesis. What is the role of photon in degradation, means organic pollutant degradation? First is three factors are depend: photochemical degradation, photothermal degradation, and photocatalytic degradation. In photochemical, when photons are absorbed by the material to chemical reaction that break down its molecular structure, and in thermal, the photon absorbed by the material causing it to heat up and potentially this material is degraded. In photocatalysis, the photon activated catalyst, then they break down a material. These are the three different materials involved in the degradation process. What is in this photocatalyst, which can be used as a organic type degradation, disinfection and cleaning, hydrocarbon, water splitting system, hydrogen evaluation, carbon dioxide production. And what is the role of metal oxide in organic pollutant degradation? In metal oxide can play important role in as a photocatalyst in a degradation of different dyes like methylene blue, rhodamine, Congo red, crystal violet, malachite green. These are the different dyes which can be used for the degradation. In photocatalysis, in metal oxide can act as electron donor or acceptor and react with the methylene blue dye to facilitate its degradation. I have used as a photocatalyst ZNO and ZRO2. In why ZNO use? ZNO as a efficient and promising candidate in the green environment system. Its unique characteristics, its wide band gap, nearly UV spectrum region, its good photocatalytic properties. And another one is it's thermally stable in N-type semiconductor. Its band gap is nearly 3 to 3.37 electron volt. And is the application means properties non-toxic, low cost, environmental friendly, and has potentially high photocatalytic properties. Another one is material ZrO2. ZrO2 is also a N-type wide band gap transition metal oxide, and its band gap is 3.3 to 5.5 electron volt. These can be vary from synthesis parameter. Therefore, the modification in structure of ZrO2 with addition of the modification of structure of ZNO with the addition of ZrO2 is strongly enhance the properties of ZNO. The increase in photocatalytic activity as compared to pure ZNO and composite ZNO ZrO2 enhance the degradation of molecule. These are I have synthesized ZNO ZrO2 nanoparticle by solution combustion method. The composite we are prepared by taking the constant ZNO and taking the zirconia as 0.2, 0.4, 0.4, 0.2, 0.4, 0.6 proportion, molar proportion. Result and discussion. First one is XRD. In this XRD, ZNO has this pattern exhibits the ZNO has strong fixed hexagonal word-side structure, and ZrO2 has tetragonal and monoclinic mix place pattern also exhibits. And I have calculated the average crystalline size by Debye-Scherrer equation. You can see that after increasing ZrO2 content, the average crystalline size increases, and the pattern confirms the formation of composite material, and also it's indicate in nanocrystalline in nature. Second is UV spectroscopy. The absorption age was obtained by UV region is 353 nanometer to 352 nanometer respectively. It is observed that with increasing concentration of ZrO2, the optical absorption decreases. The decrease in absorption correlated with the increase in band gap and increase in the particle size. And also I have calculated the optical band gap by using tau plot. The calculated band gap is increases 3.01 electron volt to 3.16 electron volt. The increasing concentration of zirconium dioxide, the band gap increases from 3 to 3.16 electron volt. Another one is characterization is FTIR. The FTIR used to identify the functional group. Normally, the metal oxide are labeled below the 1000 centimeter inverse range. In contrast, the band observed 1576 centimeter inverse are assigned to hydroxyl group, and the sharp bands observed of my material means ZNO and ZNO ZrO2 are 428 centimeter inverse to ZNO band and 619 centimeter inverse to ZNO ZrO2 band, which confirm the composite material. Another one is ACM and EDS. The ACM image of pristine ZNO and composite ZNO are labeled in ABCD diagram. The calculated nanoparticle size.
Sorry, Mr. Landge, you have 2 minutes to conclude. 8 minutes is over.
Okay. The particle size are in the range of 30 to 45 micrometer, and the decrease in agglomeration is observed due to alteration in the surface charge of ZNO particles. And the EDS also shows the elemental composition of zinc, oxygen, zirconia is as synthesized nanocomposite. Last is dye degradation. I have taken a methylene blue dye. You can see that after 240 minutes, the degradation efficiency nearly 85%. I have observed, means pure ZNO to composite ZNO, the efficiency also increases. These are the comparative analysis of my research work, pure ZNO and composite. These are the literature review. I have synthesized solution combustion method, and here this is my present work. And conclusion is the phase formation purity was confirmed using XRD and EDS. The optical absorption spectra revealed the optical band absorption spectra revealed the optical absorption and band gap energy of ZNO decreases with increase in ZRO2 content in the range of 3 to 3.1 electron volt. FTIR spectrum confirms the ZNO and ZRO2 nanocomposite. ACM images also shows the morphology of the parent compound with change in ZRO2 concentration, and the decomposition of methylene blue dye under the solar light exposure. The degradation efficiency nearly 85% was observed, and we observed. These are the bibliography. Thank you, sir.
Any question from audience side?